Hello, in this video we're going to look at the Reynolds number and in particular how this number appears naturally from the Navier-Stokes equation. Okay, so to look at the Reynolds number, we are going to take a quite unusual route, but one that is going to make it appear very naturally. So we're going to start from the Navier-Stokes equation. And this equation writes rho times du by dt plus u dot grad u equals minus the gradient of the pressure plus mu times the Laplacian of u. Okay, so this is our Navier-Stokes equation. And the first thing that we're going to do with it is what we're supposed to do with any equation that we deal with in physics, which is we were going to proceed to the non-dimensionalization. And for this non-dimensionalization, we are going to be remaining quite vague, saying that the velocity will be scaled according to a velocity scale, capital U, and that U star is going to be our rescaled velocity, our non-dimensional velocity. We are going to do the same for the position vector x. It's going to be a length scale, capital L times x star, and we're going to work with that quantity x star. The same thing will be done with the time, and there's no need to introduce any more scales for time, because we can just take as a scale for time L divided by U, which is homogeneous to a time, and therefore I'm going to have T star here. And the key thing here is that I could do something for the pressure, but I don't really know at this stage what I want to use as a non-dimensionalization for the pressure. So what I'm going to do here is rather to use capital P, a pressure scale, which I won't say anything about for a little bit. And that's going to carry the scale and the dimensions for the pressure, and therefore my P star here is a non-dimensional version of the pressure. Okay, so I've got all these terms, and I'm just going to plug that back into the Navier-Stokes equation and look at what this equation becomes for the non-dimensional quantities. So the first term here has got a rho, so that's got a rho, then there's a velocity divided by a time, so that's going to be u squared over L. Remember that the time scale is L over u, and this is du star by dt star. We're talking about these non-dimensional quantities here. Then my second term here has a rho in front of it, and that's 2 u's and 1 over L due to the Laplacian, due to the nabla operator. So that's rho u squared over L, u star dot grad star u star. And on the right hand side I'm going to have my pressure gradient here. So I've got my scale for the pressure, there's a minus sign in front of it. The gradient makes a 1 over L come in, and that's going to be gradient of my non-dimensional pressure. And my last term involved the viscous forces, which is going to be mu. There's a velocity here and a Laplacian, so I've got u divided by L squared, and this is grad squared of u star. Okay, so this is what my non-dimensional version of the Navier-Stokes equation looks like. Obviously there are all these parameters in there, so one thing that we can do to simplify a little bit this equation is to divide everything by rho u squared over L. Particularly this would give me a left hand side without any coefficient in front of it, which is always appreciable. So if I do this, then I will have du star over dt star plus u star dot grad star u star here, that's my left hand side. And for my right hand side, remember I'm dividing everything by rho u squared over L, which is our common prefactor in front of the left hand side terms. So that's going to give us minus P over rho u squared times the gradient of the pressure. And here what we're getting is some simplifications with mu here, and we are getting rho ul in the denominator times the Laplacian of u. Okay, so this is our equation. And there's two things that we want to notice here is that these terms are non-dimensional. They have no dimension. Okay, all the parameters that were in front of them have been sent to the right-hand side. So this has absolutely no dimension. Therefore, everything on the right-hand side has no dimension. So there's two things that we can notice here. First of all, we can notice this group, and by this reasoning, this group has no dimension, okay, or dimension unity. And this group has been essentially called the inverse of the Reynolds number. So for historical reason. And so this is 1 over the Reynolds number. And so we can define the Reynolds number to be rho ul over mu. Okay, so this is the definition of the Reynolds number. And you can have a sense here for what it does. It compares inertia, which is here, over the viscous forces. So if the Reynolds number is large, your flow is going to be driven by inertia, or conversely, you can imagine that the viscous forces, friction or dissipation, is weak in this flow. And conversely, if the Reynolds number is small, then that means that viscous effects dominate, and that the fluid flow is not dominated by inertia. So this is the first thing that we can notice, and the second thing that we can notice is this group here. And this group, if we want to continue simplifying further the equation and the dimension of the parameters involved in the equation, gives us with two choices, two obvious choices here. So there's two different choices for the non-dimensionalization for the pressure. So the two choices for P. The first of these choices is, it's quite obvious here, is to take P equals rho u squared, right? So we're scaling the pressure onto this scale based on the velocity, okay? And so what this is going to give us is a prefactor 1 here, all right? So this is the reason why this is an obvious choice. And the second choice is to take P equals mu u over L, and taking P equals mu u over L is going to make this term, this prefactor here, equal to the prefactor that we have here. That is to say, it's 1 of the Reynolds number. And this is useful in a sense because we can just send the Reynolds number to the left-hand side and look at the equation, look at the resulting equation. Okay, so there's these two choices. First of all, the first choice, which is P equals rho u squared, the Navier-Stokes equation then becomes, in its non-dimensional form, du star over dt star plus u star dot grad star u star. And in that case, this is 1, so that's minus the gradient of the pressure, plus, here we get 1 over the Reynolds number times the Laplacian of the velocity. So that's one way to look at it. And the second one, as I said, was to take this second equality for P. And if we do this, then our Navier-Stokes equation becomes the Reynolds number times du star over dt star plus u star dot grad star u star. And this is equal to minus grad P plus the Laplacian of u star. Okay, and so we do have these two variants for the Navier-Stokes equation. They also help us understand what this Reynolds number is. So particularly if the Reynolds number is really small, okay, so small compared to 1, what we see is that in the second version of this equation, the left-hand side then is small compared to the right-hand side. And small Reynolds number means there is no inertia in our flow, and it's dominated by viscous effect, which is a sort of consequence of the writing of the Reynolds number here. And conversely, what we can see is that if we take this time a Reynolds number that is large, we can look at this equation in particular. A Reynolds number that is large means that this term is going to be very small, and as a consequence means that the flow is driven by what is here, which is the inertial terms, rather than the viscous effects. Alright, so in this video we've seen what the Reynolds number is and how it appears naturally from non-dimensionalizing the Navier-Stokes equation. We've also discussed very briefly what flow correspond to a large and a small value of the Reynolds number. This concludes this video on the Reynolds number.